Welcome everyone to part one of a theory and intuition behind principal component analysis. What we're going to do here in part one is quickly cover the history and motivation behind the main ideas of PCA, that is principal component analysis. And then later on, we'll focus on the mathematics of PCA in part two. So principal component analysis gets its beginnings in 1901 when Karl Pearson publishes his paper on lines and planes of closest fit to systems of points in space. And that itself is based on the principal axis theorem in the field of geometry. And if that name sounds familiar, Pearson was actually the protege of Francis Galton, who was creator of linear regression, and the Pearson correlation coefficient is named after Karl Pearson. The term principal component analysis comes to widespread use in 1933 when American mathematician and economist Harold Hotelling actually independently develops and names principal component analysis in the publication Analysis of a Complex of Statistical Variables into Principal Components. It should be noted that what Pearson publishes in 1901 is essentially principal component analysis, but it's not until 1933 where we actually get the term principal component analysis. And let's take a look at this title of Hotelling's publication. Hotelling's paper actually perfectly describes the purpose of PCA, which is to analyze a complex set of variables. That is something when we talk about complex as in a highly dimensional set of features or variables, and we want to analyze it into its principal components. And we could think of analyzing as really another term for reducing into its principal components. So let's review that motivation and basic idea behind principal component analysis. Principal component analysis sets to have two outcomes. One is to just reduce the number of dimensions in the data. And recall, when I'm talking about reduce, I don't mean pick a subset, I mean actually transform the original data into a lower dimensional data set. So we should think of this as not a really reduction, but it's really a transformation of the data that just happens to reduce the actual number of dimensions of data. And we also want to show which features explain the most variance in the data. And recall, this is an unlabeled or unsupervised data technique, so we don't need labels for it. So let's talk about that first part, dimension reduction. What are we actually talking about here? Let's imagine that I have a very simple data set with just two features. With two features, that means I can easily perform a scatter plot here and analyze the relationship maybe between mean radius and mean smoothness. So what we have here is some features about some tumors that were essentially removed during a biopsy, and we took a bunch of measurements on those tumors, such as mean radius and mean smoothness, and maybe I'm just trying to figure out what actual relationships do we have here in the data. So for two features, this is easily understandable by a human because we can perform something like a scatter plot of feature 1 versus feature 2. Now when it comes to 3 dimensions, this is still within the realm of something we can plot out, either using a 3D plot, or maybe we can be a little clever and try to use color to denote some sort of third dimension. So here, even in 2 dimensions, I'm able to actually show 3 dimensions by kind of using this color trick, where the mean symmetry is the actual coloring of those scatter plot points. Now, when we go beyond 3 dimensions to maybe 4, 5, 6, or even 30 plus, such as we have here, and we will be working with this data set, how can I possibly actually visualize this amount of data? One way I could do it is try to perform a heat map just on these raw data points. But notice, I have over 500 rows. And if I were to actually perform a heat map on this, given the variety of orders of magnitude of the features, as well as how many rows I have, over 500, this is really hard for a human to just look at this data and understand the relationships between all the variety of features. So really at a certain point, it becomes impossible for a human to just figure out some sort of raw visualization in order to fully understand or get some intuition behind the data. So it would be nice if we could perform some sort of data transformation that resulted in dimension reduction. So really, dimension reduction will help us visualize and understand complex data set. Now, in conjunction with that, it can also act as a simpler data set for training data for machine learning algorithms. So sometimes it can actually be more productive to run PCA first, reduce a highly dimensional data set into its principal components, and then run your machine learning algorithm on those principal components, which are fewer and maybe helps your machine learning algorithm run faster on the smaller data set. So it can help reduce n features to a desired smaller set of components through a transformation. And just to make it very clear, I've stated this a couple of times, but it does not simply select a subset of features. Beginners to data science and machine learning often are confused with principal component analysis and think that it's grabbing some sort of subselection of columns, but that's not the case. It's using all the original features and then transforming it to some other set of dimensional components, which we'll learn about mathematically later on. Now let's talk about variance explained. We've often seen that certain features are more important or have more explanatory power than other features. For example, the size of a house is probably much more important than the color of a house when explaining the price of a house for sale. So we could say that the size of a house is probably going to explain more variance in the price of a house than the color of a house. Now, this idea of more important features is easy to understand when we can directly correlate features to a known label. But what about unlabeled data? What measurement can we use to determine feature importance or variance explained by a feature when we're dealing with unlabeled data sets? Well, we could measure the proportion to which each feature accounts for dispersion in the data set. And we would expect features that have a higher dispersion are going to explain more variance of the overall data set. So let's imagine we have this particular data set of feature 1 versus feature 2. What the idea behind principal component analysis in relation to explaining variance is to figure out, is there another way of looking at this data along some other dimension that maybe combines feature 1 and feature 2 that could both reduce the data but also explain a large amount of the original variance. For example, I could take a look along this new component or this new dimension. So we have this new axis, and keep in mind this new axis by definition has to be a combination of feature 1 and feature 2 because it exists along that two-dimensional space. So if I were to go along this black axis line, I would have some value of feature 1 and some value of feature 2, so I have some sort of linear combination of those features to create that line. Likewise, I could look at it orthogonally, or that is perpendicular, and take a look at this component. Now, if I look at the scattering of these data points along these two components that I've kind of discovered here, we have to think which one explains more of the dispersion in the data set. If I were to basically collapse all these points onto one of these components, where would I have the most dispersion remaining? Well, clearly we can see that I would probably have more dispersion or variance explained along this first one, because that's actually capturing more of the variance and dispersion of the original data set. So that means principal component analysis, for example, if we wanted to reduce from 2 features to 1 dimension, I could discover this new component, then I would reduce everything onto that new component, and I would have my principal component number 1. And what's nice about PCA, it will actually order principal components in terms of variance explained. So here, I'm reducing 2 features, that is 2 dimensions, to 1 principal component, that is 1 dimension. The principal component is a linear combination of feature 1 and feature 2. So that means I would eventually just plot this out along one axis of principal component 1. And we can do this from any number n to any other number n. So I can go from 30 original feature dimensions to maybe 5 principal components, or something like that. Here we've gone from 2 to 1. Now, principal component is a linear combination of the original features. The more variance the original feature accounts for, the more influence it's likely going to have over those principal components that are discovered by PCA. So here we went from 2 features down to 1 principal component. And this single principal component can explain some percentage of the original data. And when I say explain, I'm talking about some sort of measurement of dispersion or variance explained. For example, I could have said that 90% of the variance of the original data set could be explained by the principal components. Now, 100% of the variance in the data is explained by all the original features. So essentially, what we're doing here when we run PCA in order to reduce the number of dimensions is we are trading off some of the explained variance for less dimensions. Essentially, your entire original data set is going to explain all the possible dispersion in the data along feature 1, feature 2, feature 3, and so on. But if you decide to run PCA and reduce the number of dimensions into some new set of principal components, then you're going to have a trade-off of not being able to explain 100% of the variance in the original data set, but you'll get significant reduction in the actual size of the data by reducing the amount of dimensions. So this can be significant savings for datasets with many dimensions, but only a few strong features. So we're going to continue by exploring how principal component analysis actually works mathematically to further understand this discovery of reducing or transforming from a set of n-dimensional features to a lower set of principal components. I'll see you at the next lecture.